Have you ever, just thought about how loud a black hole merger might actually be? You sent over this research paper
Oh, yeah, yeah.
about the physics of sound,
Mm-hmm.
and it goes into this comparison between the intensity of sound
Okay.
and the intensity of gravitational waves from a black hole merger
Right.
that LIGO detected.
Yeah, it's wild.
That was crazy.
It really highlights how differently those two things interact, like sound and gravitational waves,
I know.
with our world and with our ears.
They found that black hole merger had an intensity similar to moonlight.
Yeah.
That's nuts. So why didn't we hear anything?
Well, that's the big question
Yeah.
that puzzled scientists for a long time, and it boils down to a really fundamental difference between these two types of waves.
Okay.
But to understand that, we
Right.
need to take a little deep dive into sound and decibels.
Okay, decibels.
Yeah.
I've always been a bit confused by decibels.
Yeah.
Why decibels? Why not decivolts?
Well, decibel, it's kind of a historical quirk. Bell comes from Alexander Graham Bell,
Oh, of course.
the inventor of the telephone.
Right.
And back in the early days of telephony, engineers needed a way to measure how much a signal weakened over distance.
Oh, so how much your voice would fade out over those old-timey phone lines.
Exactly.
I got it.
And dec just means 1/10, making the decibel a more convenient, smaller unit.
Okay.
But the interesting thing is they work on a logarithmic scale.
Logarithmic? How does that work again?
So think about it this way.
Okay.
A small increase in decibels represents a much larger increase in the actual intensity.
Okay.
So if you double the intensity of a sound, you only add 3 decibels.
So a 3 decibel increase means the sound is twice as intense.
That's exactly it.
Wow.
And this logarithmic nature of decibels is really important when we talk about how we perceive loudness.
Okay.
Let's say you're at a rock concert,
Okay.
blasting 110 decibels.
Right.
If you move to a spot that's 3 decibels louder, it wouldn't just sound a tiny bit louder, it'd actually sound twice as loud.
Wow, that's crazy.
Yeah.
So even small changes in decibels can make a big difference in how we experience sound.
Huge difference.
Okay.
Absolutely. And it gets even more complex because our ears, they don't perceive all frequencies equally.
That's true.
We're much more sensitive to sounds in certain frequency ranges.
Right, like how a high-pitched whine can be super annoying,
Yeah.
even if it isn't that loud.
Exactly. And that's what fawns take into account.
Okay.
Fawns are a measure of perceived loudness that factors in the frequency of a sound.
So fawns help us understand how loud something feels to us. Not
Exactly.
just its raw intensity in decibels.
You got it.
Okay.
But even fawns don't tell the whole story.
Oh, no.
Above 40 fawns, the perceived loudness, which is measured in sones,
Okay.
doubles for every 10 fawn increase.
So we've got decibels for intensity,
Right.
fawns for perceived loudness at different frequencies.
Yes.
And sones for how much louder something feels as we go up the fawn scale.
It got it.
It's a lot.
It is a lot to keep track of.
Yeah.
But understanding these concepts is super crucial to understanding why we can't hear those super powerful gravitational waves,
Right.
even though they have a calculated intensity comparable to moonlight.
Right back to those black holes.
Yes.
The paper calculated the intensity of that LIGO merger to be around 20 milliwatts per square meter,
Okay.
which you said is similar to the intensity of moonlight hitting the Earth.
Exactly.
That's crazy.
And consider the sheer amount of power involved in a black hole merger.
Oh my gosh.
We're talking about 3.6 times 10 to the 49 watts.
That's insane.
That's more energy than our sun emits in a billion years.
Oh, wow.
All compressed into a fraction of a second.
Crazy.
And remember, this was detected from a distance of 410 megaparsecs.
That's so far.
It's mind-bogglingly vast.
Yeah.
So we have this incredibly powerful event with detectable intensity reaching Earth, but we still didn't hear a peep.
So what's the explanation?
The key is that sound waves
You got
and
it.
gravitational waves are fundamentally different in how they travel through space.
So let's unpack that. How so?
Imagine sound waves like ripples spreading out when you drop a pebble in a pond.
Okay.
Those are pressure waves
Okay.
moving through a medium
Uh-huh.
like water or air.
Okay.
But gravitational waves, on the other hand,
Yeah.
are ripples in space-time itself,
Whoa.
caused by the acceleration of massive objects.
Ripples in the fabric of reality.
It is.
That's definitely a step up from pond ripples.
Yeah.
So even though both sound and gravitational waves have intensity,
Yes.
they interact with our world in totally different ways.
Completely different.
Okay.
And that difference is at the heart of why we can't hear gravitational waves.
Okay.
The paper explains that sound intensity depends on the square of something called strain. Well, gravitational wave intensity depends on the square of the strain's derivative.
Derivative as in how much something changes over a distance.
Yes, precisely.
Okay.
So this difference means that gravitational strains have very small gradients, which is another reason they don't affect us the same way sound waves do.
So the way sound and gravitational waves move through space is fundamentally different.
It is.
Leading to vastly different intensities.
Yeah.
Even for events with comparable power.
Exactly. And there's another crucial distinction.
Okay.
Gravitational waves are quadrupolar,
Uh-huh.
unlike sound waves, which are isotropic.
I'm going to need you to break that down for me.
Okay.
What does quadrupolar mean?
Think of it this way.
Okay.
Sound waves spread out uniformly in all directions, like those ripples in a pond.
Okay.
But gravitational waves have a more complex four-pole pattern.
Okay.
Imagine those ripples having a shape like a four-leaf clover.
Wow.
That's what we mean by quadrupolar.
Huh?
The waves have a more directional pattern.
So not only are they ripples in a different medium, they're also rippling in a totally different way.
Exactly.
This is all starting to make sense now.
Good.
And there's one more piece to this cosmic puzzle.
There is.
Something that delves into the very heart of modern physics.
Yeah.
Ooh, I love where this is going.
Okay.
Tell me more.
All right. So the paper touches on this really fascinating point about the quantum nature of sound
Okay.
and how it contrasts with our current understanding of gravity.
Okay, I'm going to need you to explain that one.
All right.
We've been talking about these sound waves,
Yeah.
but how does quantum physics enter the picture?
Well, think about it this way.
Okay.
At like the most fundamental level, sound arises from the interactions of tiny particles,
Okay.
atoms and molecules bumping into each other,
Uh-huh.
creating those pressure variations we perceive as sound.
Okay.
And those interactions are governed by the laws of quantum mechanics.
So even though we experience sound as these, classical waves spreading through the air,
Right.
underneath it all,
There's this whole quantum world
wow,
buzzing away, creating those pressure waves.
that's crazy.
It's kind of like realizing that the smooth surface of a lake is actually made up of countless water molecules all jiggling around.
Whoa, that puts a whole new spin on listening to music.
It does.
So how does general relativity fit into all of this?
Yeah.
We were talking about gravity and space-time earlier.
Exactly. So general relativity is our best theory for describing gravity.
Okay.
And it's what predicts those ripples in space-time, the gravitational waves.
Right.
The challenge is that general relativity and quantum mechanics haven't quite been reconciled yet.
Mm-hmm.
They're like two separate rule books for the universe,
Right.
and we haven't figured out how to merge them into one grand unified theory.
I've heard about this. It's like they're speaking different languages.
Yeah,
And physicists are still working on finding the universal translator.
it's a great analogy.
Yeah.
And that's precisely what the paper highlights. While we can trace the origins of sound back to those quantum interactions of particles, our understanding of gravity, and therefore gravitational waves, is still rooted in the realm of classical physics.
So even though we can calculate the intensity of a black hole merger
Right.
and compare it to something like moonlight,
Yeah.
we're still missing a piece of the puzzle when it comes to the underlying quantum nature of gravity itself.
It's a profound mystery.
Yeah.
It reminds us that even in something as familiar as sound, there are still deep connections to these fundamental forces of the universe that we're only beginning to understand.
It's amazing to think that something as seemingly simple as sound can lead us to such deep questions about the very nature of reality.
I know, it's pretty wild.
So let me see if I got this straight.
Okay.
Even though the black hole merger was incredibly powerful,
Yes.
we couldn't hear it
Yeah.
because gravitational waves don't interact with our world
Right.
or our ears
Yes.
the same way that sound waves do.
You got it. And it's not just our ears either.
Oh.
The instruments we use to detect gravitational waves are fundamentally different from microphones.
Okay.
They're designed to pick up those subtle ripples in space-time,
Mm-hmm.
not pressure waves in the air.
It's crazy that we've come a long way from those early decibel measurements on telephone lines to detecting ripples in space-time.
We have.
And who knows what other cosmic sounds might be out there waiting to be discovered.
That's a great question.
That's an incredible thought.
Yeah.
If we could hear gravitational waves,
Yeah.
what would the universe sound like?
Right.
Would it be this chaotic symphony of black hole mergers?
Yeah.
Or maybe a subtle hum of space-time expanding?
I don't know, those are questions that still spark debate and wonder among scientists.
Yeah.
But it is fascinating to think that we're just beginning to explore this entirely new realm of cosmic sounds.
This whole conversation has really shifted my perspective on sound.
Good.
We rely on it so much to experience the world around us, but it's only one small part of a much grander cosmic symphony.
That's a beautiful way to put it. And now that you mention it,
Yeah.
it makes me wonder, are there other examples of things out there that are loud in a scientific sense,
Wow.
but that we can't actually hear?
That's a great question.
Yeah.
I'm curious too.
Yeah.
What else might we be missing?
I don't know. Let's find out.
What else might we be missing?
Well, like lots of things.
Right.
Think about the sun.
Okay.
It's constantly radiating energy,
Right.
including electromagnetic radiation across like a wide range of frequencies.
So the sun is basically blasting out this cosmic radio show,
yeah,
and we're totally oblivious.
pretty much.
Right.
If we could somehow like hear the sun's electromagnetic emissions,
Yeah.
it would be deafening.
Oh, wow.
But our ears are simply not designed to pick up those frequencies.
That's wild.
It is.
Makes me wonder, like, what other sounds are out there that we're missing?
Right.
Maybe, like, entire galaxies are humming along to their own cosmic tunes.
It's a fascinating thought, isn't it? It kind of highlights how much of the universe remains hidden from our direct experience,
Right.
just because of the limitations of our senses.
Makes sense.
But that's what's so exciting about science.
Yeah.
We're developing new tools and technologies that allow us to listen to the cosmos in ways we never could before.
Like radio telescopes that capture those electromagnetic waves you were talking about.
Exactly.
And, of course, LIGO, which can detect those incredibly subtle tremors of gravitational waves.
Yes, exactly. And with each new discovery, we're gaining a deeper appreciation for the incredible complexity and beauty of the universe.
That's true.
Who knows what other wonders await us as we continue to push the boundaries of our understanding.
This deep dive has been an incredible journey.
It has.
From the intricacies of decibels and how we perceive sound,
Uh-huh.
to the mind-boggling power of black hole mergers,
Yeah.
and the mysteries of gravitational waves.
It's really fascinating stuff.
It's really given me a whole new perspective on this surprisingly loud universe we live in.
It is surprisingly loud when you think about it like that.
It really is.
It's been a pleasure exploring these ideas with you.
Likewise.
I hope this deep dive inspires you to keep asking questions, to keep seeking out those hidden melodies of the cosmos, and to never stop being curious about the world around us.
I definitely won't. Maybe one day we'll even figure out how to build a gravitational wave microphone.
Oh, wow.
So we can finally hear those black holes sing.
Now that would be a symphony worth listening to. Until then,
Yeah.
keep exploring, keep questioning,
I will.
and keep listening for the whispers of the universe.
Thanks for joining me on this deep dive.
It's been a pleasure.